Hello students, in this video we'll prove the Schwarz Lemma. So what is the Schwarz Lemma? It's a very powerful tool in complex analysis. And here's the setup. It says suppose that F maps the disk into C is holomorphic. With F of 0 being 0. So F vanishes at the origin, okay? If F belongs to the Schur class, and I'll tell you what that means in a second here. The Schur class is exactly those functions. Those are functions F that map the disk into the closure of the disk, right? So in other words, that's equivalent to saying that F of Z is less than or equal to 1 for modulus of Z less than 1. That's what the Schur class is. So it maps the disk into the disk, and it takes a maximum value of 1, right? So let's recall by the maximum principle, what's the conclusion? Then, what does the Schwarz Lemma tell you? Then the Schwarz Lemma tells you that the modulus of F can grow no larger than the modulus of Z. Then, modulus of F of Z less than or equal to modulus of Z for Z in D. And F prime of 0 is less than 1, like that, less than or equal to 1. Inequality holds if and only if F is constant, right? Equality holds if and only if F of Z is e to the I theta times Z for some theta. That's the Schwarz Lemma. Very powerful, very simple to state, very powerful result in complex analysis. The variants of the Schwarz Lemma in different domains actually give you lots of geometric information, okay? Excellent. So how would you prove something like this? So here's the proof. Okay. Excellent. So we know, of course, that F of 0 is 0, so F is defined as 0, right? So let's construct a function. Construct g of Z, which is F of Z over Z, and then F prime of 0 for Z not equal to 0 for Z equal to 0. So that's the function we're going to construct. Now this function g, of course, has a removable singularity at 0, right? And in particular, it's the limit existing being holomorphic at 0 implies that this exists and is continuous, right? So by Moreira's theorem, I know that this is going to be a holomorphic function. So this function g, then g, maps D into D, is a holomorphic function. Beautiful. So a holomorphic function g. And so now let's do this. Let's suppose that what? Suppose that modulus of Z is less than or equal to R, okay? Where R is less than 1, like that, okay? That's a closed disk. And so the maximum principle, by the maximum principle, what can I say about the modulus of g of z, right? Modulus of g of z is less than or equal to modulus of g of r e to the I theta for a theta, for a given value of theta, for some theta. Because what's this? This, of course, is the circle of radius r, and that's the boundary of this region, right? So we know that the absolute largest of the modulus of a holomorphic function can be is always achieved on the boundary, right? So in other words, this is the boundary values. R e to the I theta is the boundary of this closed disk over here, right? And so there's some theta that maximizes this thing. The maximum occurs on the boundary, right? So the maximum of the modulus of a holomorphic function on a closed set that's continuous there achieves its value on the boundary, right? So the maximum is achieved on the boundary. The max achieved on the boundary is what we're saying here. Okay, excellent. Good. But what does that tell me now? That tells me, so I'm going to recast this now. I know that g of z is what? G of z is f of z over z modulus g of z. less than or equal to I theta for this particular value theta. And now what is this, of course, over here? So this, of course, is just going to be f of r e to the I theta over r e to the I theta. Now f is bounded by 1, right? So this is less than or equal to 1 over r. Okay, good. This is true for all r. True for all r less than 1. So take a limit. So take r converging to 1. So if r goes to 1, what does this tell me? This tells me that if modulus of z is less than 1, this implies what? This implies that f of z over z is less than or equal to 1. And this implies, of course, what? That says that f of z is less than or equal to modulus of z. Okay. Now, what happens if we have equality over here, right? So in other words, if there was an interior maximum of this function g, that would say that g is constant, right? If equality happens anywhere at any point in time, if equality happens anytime, if equality happens then g is constant. G of z is constant, right? And that constant has to be equal to 1, right? So it has to be a unimodular thing, like this over here. G of e to the I theta. G is constant, right? And if that's the case, then that says that f of z, then f of z is e to the I theta times z, as we assumed over here, right? And of course, the corollary is as z goes to 0, that goes to the derivative at 0, right? And that's less than 1 also, so that trivially follows. Okay, excellent. Now we get one sort of really special case of this, and so we'll talk about that special case. So recall, definition, phi, mapping d to d, holomorphic and bijective, and bijective, I mean injective and surjective, implies that phi is called an automorphism. Okay. Good. And of course, there's two special cases of automorphism. Now look at this class of automorphisms. Rho of theta of z is just e to the I theta z. That's a rotation, and that rotation is clearly an automorphism of the disk. And we also have these other special ones, right? Our Blaschkes, right? Ba of z. I'm going to modify it a little bit. I'm going to say a minus z instead of z minus a, so it's its own inverse now. That's an automorphism of the disk, right? So those are two classes of automorphisms. For every theta, this is an automorphism, and for every a, this is an automorphism of the disk, provided, of course, that a is where. So a has to be in the disk for this to be an automorphism. I claim that all automorphisms are just compositions of these two things, right? And so how do we prove something like that? So suppose, if phi maps d to d an automorphism, then phi has to map some point to 0, right? So phi of a has to be 0 for some value of a, right? In other words, so only one value goes to 0, right? And what I'm going to do is I'm going to construct phi, good. And so let's look at this function over here, psi of z, which is what? Which is phi composed with ba of z, right? Let's look at this function over here. And then what's phi of 0? Phi of 0 is b of 0 is a, and phi of a is 0, so that says that phi, so this maps the disk to the disk, and phi of 0 is equal to 0. So by Schwarz, phi of z is less than or equal to modulus of z, okay? Good. But the same thing is true if phi is an automorphism of the disk, so is phi inverse, because automorphisms are invertible, right? And so this also implies, that modulus of psi inverse of z is less than or equal to z like this, right? And so in particular, these two inequalities together, if I plug these in, tell me what? They tell me that automatically, so I can plug in psi, and I can plug in psi inverse to this too, right? So I can reverse this inequality. So I can plug in what over here? I can plug in psi inverse and get that modulus of z is less than or equal to modulus of psi inverse of z, right? And I can play the same game, right? So that forces, of course, these two inequalities force psi of z to be unimodular. Psi of z is equal to z. Good, for all z, which means that psi is constant, right? So psi is unimodular. Good. So psi of z is a rotation, is e to the I theta times z. And that says that if I do the inverse of this thing, that phi is what? Phi is going to be a black, because BA inverse is this, is going to be a rotation. So it's going to be some rotation. Let's call it rho theta composed with BA over there. So in other words, we've just shown that every conformal automorphism of the unit disk is a composition of a rotation in a single Blaschke factor. Very, very useful result. So I've completely classified all the conformal automorphisms of the unit disk. This methodology will allow me to look at other classes of conformal automorphisms for domains which are conformally equivalent to the unit disk, of which there are many, and that's a prototypical example of what we want to consider. So from this very, very useful application of the maximum principle, the Schwarz lemma allows me to classify all the automorphisms of the disk. And we'll see that this gives us a lot of useful geometric applications in further videos. Thank you very much.